So today we are moving on. We're kind of combining the things that we've done with, synthetic division, our complex numbers, and we're all throwing it together now finally for polynomials. Okay, finding zeros of polynomials more specifically. The first thing we have here is what's the fundamental theorem of algebra. What that says is f of x is a polynomial of degree n, okay, and n is some positive number greater than 0, usually a whole number. Then the function f has at least one 0 in the complex number system. We've learned something similar before, that if a polynomial function has a degree n, then there are n zeros. Okay, so we talked about sometimes, we have quadratics, some parabolas that don't cross the x-axis, right? So those would have one or two complex zeros. Also remember that technically a real number is a complex number that doesn't have the imaginary part. Okay, so we have, a plus bi is our complex number. If b is 0, it's still a complex number. It just doesn't have the imaginary part. Okay. Yeah, so it's like the real numbers are, it's called a subset in the complex numbers. So you have all your complex numbers, that's one big circle, and then the real numbers are inside of that. So that brings us to our linear factorization theorem. So we have, again, f of x, some polynomial function of degree n. Then it has precisely n linear factors. So now we're even breaking up even further and saying that we can break it up with complex numbers to only linear terms. Okay, previously we may have been stopped because there was no real numbers that we could break it up to. Okay, just for example, all right, say we did some polynomial division, we found some of our roots, but then we were left with x squared plus x plus 1. Well, this doesn't have any real roots. If I graphed this, it would be above the x-axis. There's no way to factor this. There's no two numbers that multiply to positive 1 and add to positive 1, right? So you can't break it down like that. But you would be able to break it down linearly if we had complex numbers, right? And that's what today and tomorrow we're going to learn how to do. All right, is everybody good with these two theorems? Can I move on, or do you need a little more time? I will take your silence as okay. So the first thing we're going to utilize is something called the rational zero test. I'm recording, right? Yeah. Okay, so we have some polynomial. It could be however long. Okay, so again, that's just saying here, this is our starting point. This is our constant, our ending point. Okay, and we have a bit of a restriction here. Okay, it has to have integer coefficients. So again, going back to numbers, integers are whole numbers. Okay, that also include negatives. So you can't have fractions, you can't have square roots, all right, as long as they're only whole number coefficients. Okay. So again, for some polynomial that has integer coefficients, then every rational zero of f has the form p over q, where p is a factor of your constant term, a naught, and q is a factor of your leading coefficient, an. So we can find rational zeros. So again, remember a rational number, which is a little different than what we've been talking about. A rational number is any number that can be represented as a fraction, right? So whole numbers are rational numbers where the denominator is 1. Okay, something like the square root of 2 is not rational because that's a repeating decimal and you can't represent it as a fraction. Okay, so all you need is the leading coefficient and the final constant number, and you can find the possible rational zeros of a polynomial. Okay, so write this down, and then, what does this mean? We'll talk about it. Okay, so we're going to take a look at a cubic polynomial here. All we're doing is finding the possible rational zeros. Okay, so right now, we're not going to take it as the step is actually finding the zeros. These are just the possible rational zeros. All right, so the first thing you're going to do is you're going to figure out your coefficients, okay, for your p and q factors. So what is our leading coefficient? Okay, so the first number you're going to look at is the number that's in the front. If we don't see a number there, then it's going to be 1, which is good. All right, if that's our case, then that makes things a little easier for us. Our constant term, a naught, is the last number. That's going to be 4. All right, so now what we have to do is we have to find factors for these numbers. Nope, switch that. This is Q. So what we have to consider too is that they could be anything positive or negative. Okay, so what are the factors of 1? Well, that's going to be a positive or a negative 1. Those are the only factors of 1. What are my factors of 4? What multiplies to 4?
2 and 2.
2 and 2. 2 and 2 and
1 and 4.
1 and 4. 1 and 4. Okay, so our first step, we're just going to list our factors. So here I have 2 options for Q. I can pick either positive 1 or negative 1. I have 6 options for P. Positive 1, positive 2, positive 4, negative 1, negative 2, negative 4. Okay, so then I just plug all those different numbers into this. Now, this is kind of done in a few different ways. You can write them all out at once. Okay, so you can write it. Okay, so in the numerator, remember the P goes. Okay, so you could put positive -1, plus -2, plus -4. And then in the denominator, you would just put all the factors of your Q, which in this case are just 1. So this step isn't necessary, okay? But when we have a lot of factors, it's good to write it like this to kind of organize everything. But what we want is all the separate ones. So for every comma, we do a separate factor. So for the first comma, we're going to have 1 over 1. So that's a plus or minus 1. Then we have 2 over 1. So that's plus or minus 2. And then 4 over 1. So that's plus or minus 4. Okay. So that's telling us that this polynomial function has 6 possible factors. All right. So you'll have something like this tonight for homework. All right. But what we do with this, okay, is now we want to find out, are they zeros? Are they actual factors? All right. So if it is a 0, when we plug it in, well, we'll get 0. So you would go in, and now we have 2 methods. You could go in and you can plug these in, right, just as you see it. And if you get a 0, then it's good. Or you can use synthetic division and the remainder theorem to figure it out, right? So you'd plug in, 1. You would plug in the coefficients, all right? So I'm going to skip that for now because this one, okay, this one in particular doesn't have any rational zeros. But let's take a quick look because let me type it out. X to the third plus 2x squared minus 6x plus 4. Okay, so here's the graph of our function. And you're saying, oh, Mr. Murray, though, we didn't find any rational zeros, but it does have a 0. Okay, that's fine. It's going to have some complex zeros because it only has one solution. But if we zoom in, right? And I hover over this, my 0 is at negative 3.836, and I'm sure if they gave us more decimals, that number would keep going. This is a 0, but it is not a rational 0. Okay, it's a real number, okay, because it's on the number line. It's not an imaginary or complex number, but it's not a rational 0. It may be, you know, the square root of, well, it can't be the square root because it's a negative answer. It may be the cube root of, I don't know, 10 or something like that. Oh, no, I'm sorry, probably be higher than that. Cube root of 30. Right? When you do that, you're not going to get a nice even number, okay, but it is a real answer. Okay, so let's take a look at an example where we do get a 0 and what happens. How much time we got? Ooh, okay. Everybody's good with this. I can move on. Oh, -6. Okay, so I'm going to give you guys a few minutes. I want you to use the PQ method to find the possible zeros, the possible rational zeros of our polynomial here. I'll give you your cue since that's easy. All right, just because we're running a little short on time. So our factors of 6. So normally we like to write these in numerical order. Okay, it's not the end of the world if you don't. All right, but we have 4 factors of 6. Okay, so we're going to have 8 possible zeros. So, you know, if we put it in fraction form, we're going to have 1 over 1, 2 over 1, 3 over 1, and 6 over 1. We have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So for the next step, unfortunately right now, it's kind of going to be a guess and check. All right, so we want to find which ones are solutions. So my suggestion would be synthetic division. Okay, so you would just pick one of these. Okay, so you could pick +1, -1, +2, -2, +3, -3, so on and so forth. Right? I'm going to take a guess. It's going to be a real lucky guess, and I'm going to guess. Let's start with -1. Right, so we write down the coefficients: 1, -1, +1, -3, -6. Right, and we do our synthetic division. Bring it down, -1, -2, +2, 3, -3, -6, +6, 0. Okay, so x equals -1 is a solution because of our remainder theorem, right? Our remainder is 0, then it's a 0. So that means I have a factor of x plus 1. Right? So then I could rewrite this as x plus 1 times, now remember, this was x to the 4th, so we're going to drop this down to x to the 3rd minus 2x squared plus 3x minus 6. Now I could try to find another factor. Okay, I'm going to take another lucky guess. I'm going to try 2. All right, so again, now, like we did way back when we were doing synthetic division, I don't have to use these coefficients. I could go back and I could use these coefficients because it makes it a little easier on us. And so we bring down the 1. 1 times 2 is 2. We get a 0. 2 times 0 is 0. We get 3. 2 times 3 is 6. Oh, we get a 0 again. So x equals 2 is a solution, which means x minus 2 is our factor. So then I would have x plus 1 times x minus 2. Now this was a x to the 3rd, so we have to drop this to x squared. There wouldn't be any x term, right? But I'll put plus 0x plus 3. All right, so the function that we started with, x to the 4th minus x third, blah, 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 can be rewritten as those. Okay, so here we have 2 rational zeros, and then here this would give us 2 imaginary zeros. And we're running short on time, so I'll show you how we continue with that tomorrow. Okay, any questions? All right, so for homework tonight, I'm not going to ask you to do this right now because we're not completely done with it. But what I am going to ask you to do is I'm going to give you 2 or 3 polynomials, and you're going to tell me the possible zeros of that polynomial. I'm not sure. I don't think you have a plus or minus key. All right, so just I don't know, type them in separately, I guess. All right, so for this, you would type in 1, -1, 2, -2, 3, -3, 6, -6. Okay, so I'm going to ask you for the possible rational zeros, and then that's how you're going to answer it. All right, guys, so take a look out for that. And then we'll continue. We'll go over that tomorrow, and we'll move on with fully factoring everything.